Okay, welcome to lecture here. We'll continue on talking about types of reactions. Okay, so last time we talked about some different types of reactions. We really talked about sort of one big classification of reactions, which is double displacement reactions. So as we saw, sort of double displacement reactions is definitely when you have two ionic compounds and basically the two positive guys will switch partners. And that's a sort of one classification of those type of reactions. Specific types of double displacement reactions sort of fall underneath that big umbrella. And we saw ones like precipitation reactions, and that's when we mix two solutions together and form some type of precipitate. So when that double exchange happens, one of the products, based on solubility rules that we saw, ends up being a solid. We also saw with that you could write several types of reactions, molecular equations, total ionic equations, and net ionic equations to describe what's going on in that type of reaction. In addition, we saw acid-base reactions, which are really double displacement reactions, acid-base neutralization reactions, which basically the overall reaction that takes place when you mix a strong acid and strong base together is the formation of water. So that's why we sometimes call that a neutralization reaction. And that's also really a double displacement reaction, but sometimes classified as an acid-base reaction. And lastly, we saw some double displacement reactions that basically will generate some gases as a result of that, either directly or indirectly. Again, a direct route of sort of forming a gas. It's just when we switch those two ions together, basically will form a gas. And sort of an indirect route is something like when we form like carbonic acid, sulfurous acid, something like that, where that one product will then go through a decomposition reaction and decompose. So like in the case of carbonic acid, it will decompose into CO2 and water, generating CO2, which obviously is a gas. And a more indirect route, again, sort of a double displacement reaction followed by a decomposition reaction. So you can classify, as we've seen, several reactions in different ways depending on sort of the aspect you're looking at. So you could kind of think again as double displacement reactions as sort of the big umbrella for with more specific type of double displacement reactions occur. Any questions on those reactions or molecular equations, total ionic equations, net ionic equations, or stuff that we talked about last time? So the next sort of big group of reactions that we're going to talk about are what are referred to as redox reactions. And they're sometimes referred to as redox reactions. And basically redox reactions stands for what we see here, which is oxidation and reduction reactions. And this usually involves a transfer of electrons when we have a redox reaction. And those two things always occur together. So if something gets oxidized, then something gets reduced and vice versa. So if something gets reduced, something definitely will go through oxidation. So they always sort of occur together, both of those processes. So let's talk about really what each of those sort of means. So when something goes through an oxidation, there's several different definitions of oxidation, but usually for sort of general chemistry, we talk about it in terms of losing electrons. So when something loses electrons, that is definitely a definition of something going through oxidation. And reduction, on the other hand, is when something gains electrons. So the gaining of electrons is reduction. Sometimes people remember that as Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. put them both together. You don't have to choose, but Leo the lion on the oil rig and he goes grr. You don't have to choose. You got all of them together there. And this is the common sort of definition in terms of oxidation and reduction. There's also other definitions in terms of oxidation. It involves, for example, the gaining of oxygen as you go from reactants to products, or it could be the loss of hydrogen as you go from reactants to products. So those are two other definitions of oxidation. We don't really get too much into those definitions. If you continue on to take organic chemistry, I'm sorry about that if you have to. If you continue on to take organic chemistry, you will see those definitions come up. They come up a lot more with sort of non-metal and non-metal. And in terms of reduction, it's sort of the opposite there. Another couple of definitions of reduction is basically the opposite of that. When you lose oxygen from reactants to products, or you gain hydrogen from reactants to products. So again, for us, probably more so the electrons is definitely probably what we deal with the most, and usually in general chemistry. But those are two other sort of definitions which are important to sort of keep track of. So when we look at a reaction like this and we look at an oxidation and reduction reaction, we can basically identify them or break them up into what are sometimes referred to as half reactions. And a half reaction for oxidation, it looks something like this. We have magnesium here. It has no oxidation state. It's zero. Remember, things that are just by themselves really don't have any charge or anything like that. The magnesium here does have a +2 oxidation state. And that means that it has lost electrons. And that's why we see electrons on the product side. So when we see electrons on the product side, that indicates an oxidation reaction happening. While if we look at the oxygen here, the O2 is this natural way it comes, has no charge or oxidation state. The oxygen here has -2, so it's actually gaining electrons here in this half reaction, and that's why it's referred to as the reduction half reaction. They're called half reactions because essentially if you put them together and add them together, and if we add both of these guys together, basically everything on the left-hand side of the arrow stays on the left, everything on the right-hand side of the arrow stays on the right-hand side of the arrow. And when we look on the left and right-hand side, there's 4 electrons on the left and 4 on the right, which can cancel each other out. And that gives us our overall reaction here, which is 2 magnesiums plus oxygen making 2 magnesium oxides. This is essentially what happens when we have a metal and a non-metal coming together. That's always what happens. The metals, right, lose electrons. They become positively charged. Our cations and our non-metals are the guys that really gain electrons, become negatively charged. And this is one of the sort of the driving forces for a chemical reaction to occur. So we have actually seen now 3 of the driving forces for an actual chemical reaction to occur. And when we talk about sort of those driving forces, the 2 that we saw actually earlier involved those double displacement reactions. The formation of a precipitate, the formation of water are 2 really big driving forces for chemical reactions to take place. And the last really driving force is an electron transfer. So these 3 things are really the 3 sort of driving forces that for chemical reactions basically to take place. Precipitate to form, water to form, which are under our sort of double displacement reactions, and electron transfers to occur, which pretty much is what's happening in this type of reactions, which are our redox reactions. Any questions on that? So sometimes people have a really hard time trying to figure out, you know, what is being oxidized, what is being reduced. So again, that's a good way to remember it is through that, but an even easier or maybe better way to sort of figure out what is happening in terms of oxidation or reduction is you could actually just lay up just a regular old classic number line here with like 0 in the middle. And to the right of 0 usually are positive numbers, to the left are negative numbers. And when something goes through oxidation, they lose electrons, which, as we know, when you lose electrons, you become more positive. So if the change in the oxidation state or the charge results in something becoming more positive, that is definitely something going through oxidation. While if you gain electrons, you're going to become more negative. So if you're sort of moving to the left here on the number line, that is something that is going through reduction. So if you just think about the two things we saw there, the magnesium went to magnesium with a +2. So it started at 0, basically, and ended at +2, which would be going in this direction. Thus, the magnesium was going through oxidation. Oxygen started at 0, ended at -2. Again, for the oxygen, started at 0, headed to the left, and went through reduction. So a very simple number line and literally just drawing which way it's going. It's a really good way to basically figure out what's going through oxidation and what is being reduced. These are some oxidation reduction reactions. This is what happens in electrochemistry. You have a whole chapter on that in 200B if you take it. And basically what happens when we get something with charge, all of our guys that have charges are in the solution part. So everything in the solution part are the guys that are swimming around. When those guys become solid with no charge, they basically come out of solution, which is all this discoloration we see here. So in this particular case, that is the copper that is coming out of solution. And the copper is coming out of solution from a +2 charge to solid copper. So we're kind of like plating the copper on this zinc. And vice versa over here, we have the opposite happening. We have sort of the copper, the zinc's coming out into solution on the other side. So this is sort of a reduction reaction. So for example, if we were looking at, say, copper 2 going to copper with no charge. So something going from +2 to 0. Again, if we sort of look at our number line here, +2 would be over here on this side, heading to 0 would be going in this direction to the left. And we would know that this is going through reduction. While if we had, say, zinc that was going to zinc with a +2 charge, zinc over here has 0, +2. Again, starting at 0, heading to +2 would be going in the right direction, and that would be oxidation that's occurring. So again, a very sort of simple way that you can figure out what's being oxidized and what is being reduced. In addition to things that are being oxidized and being reduced, we also have what are referred to as the oxidizing agents and the reducing agents, which sometimes confuses people as well. So when we look at this particular reaction here, let's take a look at really what's happening in this reaction all the way across. When we have the zinc that's over here, this zinc is 0. Again, by itself, uncombined, has an oxidation state of 0. This copper here is copper 2 sulfate, has a +2 charge. This whole sulfate is -1, so I'll just do a big minus over it. On the right-hand side, our zinc is +2. Our sulfate is also -1, and our copper here has, again, no charge. So as we just did there on our little number line there, we saw the zinc go from 0 to +2. Again, heading in the right direction there, which means it's going through oxidation, which is why we have our half reaction written like so. Zinc going to zinc with +2 charge, again, oxidation, electrons on the product side, while our copper going from +2 to 0, again, starting at +2 over here, heading to the left, going towards 0, meaning it's going through reduction. And that's, again, what we see here. Copper with a +2 charge gains the 2 electrons. Electrons on the reactant side going to be our reduction half reactions. Again, if we take these together, and whenever you add together these half reactions, the one thing that you should always make sure is the same is the number of electrons. So the number of electrons in each half reaction has to be the exact same number. If they are not, you may have to multiply a half reaction by a number to get everybody to the same number of electrons. The reason for that is because oxidation and reduction happen together. However many electrons are lost by one thing should be how many electrons are gained by something else. So the number of electrons in each half reaction should always be the same. And when we would add this together, again, everything on the left-hand side of the arrow stays on the left-hand side. Everything on the right-hand side of the arrow stays on the right-hand side. And again, you can think of the arrow as like an equal sign. So if you subtract the 2 electrons from each side, they cancel. And we would be left with the overall reaction that's really happening here, which is this. And this is really our net ionic equation for what's happening. This is our zinc going to zinc 2 plus, our copper 2 going to copper with no charge. And you may be asking, what about the sulfate here? So the sulfate here, again, is really a spectator ion in this case. So if you actually had the sulfate in there, nothing's happening with the sulfate. It's really just a spectator ion. And this is really what's happening, the zinc going from one to the next. Now, when we talk about reducing agents and oxidizing agents, they are opposite of the name. So what I mean by that is the reducing agent is the thing that actually gets oxidized. So the reducing agent is the substance that goes through oxidation, while the oxidizing agent is the substance that goes through reduction. They are opposite in their names in terms of what is actually happening. And that is because in order for something to get reduced, it has to gain electrons. In order for it to gain electrons, it has to cause the oxidation in something else. So the thing going through reduction, which will gain those electrons, has to cause something else to lose them and be oxidized. And that is why the oxidizing agent is the thing that gets reduced. While if something is getting oxidized, that means somebody else will gain the electrons and they will get reduced. So they're called those things because they cause the opposite effect in the other substance. And that is why here, when we look at zinc, this is the zinc that is going through oxidation, and this is actually our reducing agent. So that is our reducing agent in this particular case. It is not just zinc, like zinc sulfate, zinc with a +2 charge. It is actually this zinc here with no charge. So sometimes people will just write zinc, and that's a good way to get a line through it, because I don't know if you're talking about this zinc or that zinc. So you do want to be really specific when you identify the reducing agent and the oxidizing agent. The oxidizing agent is actually the copper 2 that's here. And it's actually this guy that's the oxidizing agent. Again, it is that copper 2 that is going to gain the electrons and cause the oxidation of the zinc. So if you have to identify the oxidizing agent or the reducing agent, it is usually found on the reactant side of the equation. Any questions on that there? Okay, so let's take a look at this one here. Copper wire reacts with silver nitrate to form silver metal. What is the oxidizing agent? So if we were to write the reaction for this, it would be this reaction here. Copper wire is solid copper. Again, no charge when it is by itself. So the oxidation state here, let's get rid of that so you guys can write it. So if we look at the oxidation states of this guy, again, the copper here by itself, oxidation state of 0. The silver here is +1. Nitrate altogether is -1. Copper on the right-hand side is +2 in this case. Nitrate is -1. And the silver here is 0 on the right-hand side. Again, by itself, not much happening with it. So if we just kind of look at our sort of number line here and see what's going on, we have copper that's going from 0 on the left-hand side to +2 on the right-hand side. So essentially it's starting at 0 and heading to +2, which means it's going to the right, which means copper should be going through oxidation. While our silver is starting at +1, which would be like over here, and it's ending at 0, which means it is moving to the left-hand side, and that is reduction when it moves in that direction. And our silver here would be going through reduction. Nitrate is -1 here and -1 here. Not much happening in terms of its charge. So if we were to write our half reactions, we would have our copper going to copper 2, and we should have a couple of electrons coming off on our product side. This again is our oxidation half reaction. For the reduction half reaction, we would have our couple of silvers with a +1 charge gaining 2 electrons and making 2 silvers with no charge on the opposite side here. And again, going from +1 to 0, and this would be an oxidation, this would be a reduction half reaction. Now, in this particular case, if we wanted to add these two half reactions together, we have our copper going to copper with a +2 and 2 electrons. We have our silver with an electron going to our silver with no charge. Before we could add these together, because we do not have the same number of electrons in each, we do need to multiply the silver guy by 2 electrons. And if we do that, we will get 2, 2, and 2. And that will cause those electrons to cancel out, which you need to always happen. So electrons should always cancel out. And what we have on the left-hand side of the arrow stays on the left. So that is copper with solid. That's a couple of silvers, giving us a copper with a +2 and a couple of silvers with no charge and a solid on this side. This is, again, our net ionic equation for what is happening here in this redox reaction. Ultimately, what is happening is copper is going from 0 to +2, losing electrons. Silver is going from +1 to 0, gaining electrons. Nitrate is really a spectator ion, nothing happening with it. So the answer to the question here is, what is the oxidizing agent? The oxidizing agent, again, is the thing that is going through reduction. So it would be the silver here. That is our oxidizing agent. And it is the silver with a +1 charge would be our oxidizing agent. It is this silver right here is our oxidizing agent. Not the silver with no charge. That is the result of it. So the silver with a +1 charge is the thing going through reduction, and it would be our oxidizing agent. Our reducing agent in that case would be the copper here. So this would be our reducing agent, the copper on this side. Any questions on that there? So oxidation, something loses electrons. The thing that loses electrons is also known as the reducing agent. The reduction is something that will gain electrons. The substance that is going through reduction is also known as the oxidizing agent. Again, those agents are always found on the reactant side of the arrow. Any questions on any part of that there? So using that number line is a good way to sort of figure out what is being oxidized, what is being reduced. And what helps us really sort of understand that is what is known as oxidation number. So we're going to talk about oxidation number here and how to assign oxidation numbers. These are also sometimes referred to as oxidation states. So oxidation number, oxidation states, kind of the same deal. It is essentially the charge that the molecule would have or an ionic compound if we had really a complete transfer of electrons, really based on sort of what it is bound to, what is it attached to, what the charge would be. So the first rule in sort of assigning oxidation numbers is any element that is in its free sort of natural form that hasn't combined with anything will have an oxidation number of 0. So that's why earlier when we saw zinc with no charge and it was a solid, it has an oxidation state of 0. This piece of sodium metal that's by itself, not combined with anything, has no charge and has an oxidation state of 0. Also, our gases or diatomic molecules like H2, N2, O2, those guys, those are naturally how they come. They come as 2s, and they also would have an oxidation number of 0. If you have a monoatomic ion, it will normally have the same oxidation number as its charge. So things like sodium with a +1 charge would be +1. Lithium with a +1 charge would also be +1. If you had iron 3 chloride, the iron would be +3 and have an oxidation state of +3 as well. Oxygen, which is usually a pretty good place to start, usually has an oxidation number of -2. And when you do give oxidation numbers, it is important to also include the positive or the negative with the numbers. So it is always important that when you state an oxidation number, even if it's +3, that you don't just write 3, you write +3 as part of the oxidation number. So you do want to make sure that you include the actual charges that go with those guys as well. As I mentioned, a lot of things that involve oxidation and reduction involves oxygen. And that's really why, as we talked about earlier, one of the definitions of oxidation is gaining oxygen. So a lot of times oxygen are involved in these type of reactions. So that's usually a pretty good place to start with when you're looking to assign oxidation numbers of things, is to start with the oxygen. And it is usually -2, like I said. There is I don't want to say rare case, but there is a case where oxygen will not be -2, and it really is this case right here. It is if it is peroxide, and this is actually peroxide right here. This is a polyatomic ion, which is peroxide. And in this particular case, the oxygen would be -1. So something like hydrogen peroxide here, the oxidation state of oxygen is -1, not -2. How do you know it is peroxide or not in that case? Usually you'll see kind of like an extra 2 like on the bottom, and that's usually a lot of times how you could kind of recognize it. Not 100% of the time, but that's a good way to think about it. So I would start with oxygen if you got oxygen involved. If you got 3 sort of letters involved or elements involved, you usually start with oxygen, you go to the other side. You usually leave the element in the middle for the end in terms of assigning oxidation states, kind of go outside, and then come to the middle when you're trying to assign oxidation states. That's usually a pretty good approach to that. Now, a few other important rules. When we talk about hydrogen, the oxidation state of hydrogen is usually +1. The only exception is if it's in a binary compound and pretty much comes after a metal. So if it comes after a metal, it's pretty much hydride, which is -1. So for example, if we had LiH in this particular case, the oxidation state would be -1 for hydrogen here. Again, because it follows a metal, the metal would be +1, hydrogen would be -1 in this particular case. Everybody in group 1 will have +1. Everybody in group 2 will be +2, and fluorine will be -1 in terms of its oxidation number. When you add up all the oxidation numbers for either a molecule or an ion, they do need to add up to the overall charge there is. So if something is neutral, then it should add up to 0. If something obviously has a -2 charge, when you add up all your oxidation numbers, they should end up being whatever I just said there, -2, I think, yes. And lastly, most of the time oxidation numbers are going to be sort of whole numbers, but they may not be. They can be, like a fraction as you have there. So something like superoxide has an oxidation state of -0.5, can technically be like a decimal, if you will. But most of the time you'll come across whole numbers, but it doesn't always have to be. Any questions on that there? So let's, yeah.
I had a question. So are there oxidation on like ionic compounds, and things like just ions, like monatomic ions? or is it on covalent as well, like ammonium?
Yeah, it's like you could apply oxidation numbers basically to anything. So ionic, non-ionic type of guys as well. So for example, if you had like sodium chloride, the sodium oxidation state would be +1 and the chlorine would be -1. If you had something like carbonate or something like that, you could do it for each of the elements that are there. So you could really apply it to either thing, either ionic or a molecular or covalent compound. Other questions? Okay.
How would you do carbonate?
We're gonna do some examples right now, so we'll hit some of those. And
Okay, thank you.
all right, so we got HCO3. So let's take a look how we would approach this guy right here. So again, in this particular case, what we want to do is, like I said, if there's oxygen involved, we would want to start with oxygen. So oxygen's oxidation state is -2. And there are 3 of them, which gives us a grand total of -6 happening here with the oxygen. Like I said, in a situation where you got kind of 3 of them, I would go to the other side next, and the other side next would be +1. That's hydrogen. So at this point, we have +1 for the hydrogen. We have -6 for all of the oxygens that are there. Now, when it says it needs to add up to the overall charge, this is bicarbonate, so it does need to equal -1 overall. So to get us to -1, the carbon here should have an oxidation state of +4 in this case, right? So it should have an oxidation state there of +4. So if we take +1 and +4, that's +5, and -6 leaves us a -1 in terms of its overall charge. Now, it's really important, and this is where people sometimes also kind of screw up here. If you're asked what are the oxidation numbers of these guys, for hydrogen, you should write +1, again with the charge. For carbon, you should write +4. And for oxygen, you should write -2. Again, not the grand total, which is what a lot of people will like to do. It is what the element would be if you just individually took it out. And in this case, it should be -2. Question on that one. So the earlier question was something, for example, like carbonate, right? So if we look at carbonate, CO3, 2-. So why don't you try this and see what the oxidation numbers are for carbonate here? And while we're talking about other polyatomic ions, let's do NO3-. And why don't we do SO4, 2-. What are the oxidation numbers of each of those elements in each of these guys here? Why don't you take a minute or two and come up with it?
Can I ask why did you circle the minus for the carbonic acid? The charge? You muted. Wait, I can't hear you.
I should probably turn that on. Huh? So
Okay.
when you that better? I don't know if that's better or not. No, if you hear me.
Yeah, it's better.
When you add up all the oxidation states, it needs to equal the charge on the molecular ion. So in this case, bicarbonate has an overall charge of -1. So when we added up all the oxidation numbers to kind of really help us figure out what the center guy was, it needs to equal -1. So that's why we know. Yeah.
Got it. Thank you.
Yeah, just like if you had something that was neutral, it needs to add up to 0. Okay, so let's take a look here. I'm just going to flip the page so I got some more room to write on, I think. So I'll just do it right here. So we had CO3 2 minus, NO3 minus, and we had sulfate, which is SO4 2 minus. All right, so again, in this case, we would want to start with the oxygen. Oxygen is going to be -2 in this case. We have 3 of them. So again, we're going to have -6. So because this is an ion, the overall charge is -2. So it does need to add up to -2 in this particular case. That means, again, here to get us to -2, +4 would be the oxidation state here of carbon and carbonate. And that's, again, why it has a -2 charge. Carbon is really +4 in this case. The oxygen in this case is -2 in terms of its oxidation number. If we go to nitrate, nitrate is -2 for the oxygen. Again, good place to start. This case, we have a -1 overall charge, so it doesn't equal -1. And in this particular case, to get us there, the nitrogen does need to be +5 in this case. So nitrogen is +5. And oxygen here is -2. And lastly, here we have our sulfate. Again, oxygen -2. That is -8 for the oxygens altogether. Does need to equal -2 as that's the overall charge. That is a lot of math there, but I can go with +6 and hope for the best there on that. So sulfur needs to be +6 in this case. And oxygen here again would be -2 as the correct way to identify the oxidation states. First off, question on any of those. Now you may say to yourself, hey, I think I remember somebody saying like nitrogen is -3 and sulfur is -6. And that is normally what the normal charges and very common oxidation number is. But as you can see from this table here, and I think you have a similar one probably in your book as well, elements can have a variety of different oxidation states. For example, here's our nitrogen. Might be hard to see on your side or not, but there are some that are in sort of a red color. And most commonly, those are the common oxidation states that you see. You can see -3 is a red one, so it's actually +5 that we just did there. But there are normal oxidation states that things normally will have in terms of their charge. And there are obviously oxidation states where things that we normally think about as being negatively charged could actually be positively charged. Also in our sort of transition metal region, our Mn is a big one. He's got like a ton of different oxidation numbers that it can be. And so oxidation number is not 100% exactly the same as the charge that we normally associate with it, but they are sort of similar. So it really does have to do with sort of what that element is hooked up with as to sort of what its oxidation state would be. In this case, when we get these two nonmetals together and they're going to share electrons, the nitrogen in that sort of situation basically takes on a +5 sort of characteristic. And that's different than if you threw that nitrogen with a sodium. With that deal, he would take on a more -3s type of charge because he's going to be able to pretty much just pick up those electrons from the sodium. Because of the similar properties between our nonmetals, they're really not going to be able to pick up all those electrons. But in terms of electronegativity, oxygen is more electronegative, right? And that makes some polar bonds. So it's going to kind of draw those electrons sort of away from the nitrogen and giving it a more positive sort of charge, if you will, or oxidation state in that case. Because in that case, the nitrogen and oxygen are two nonmetals that share very similar sort of periodic properties that we talked about, as opposed to when that nitrogen hooks up with a metal, it's going to do what we normally think about metal and non-metal. It's just going to grab those electrons because there's a big difference in those periodic trends. So obviously oxidation states of elements are affected by, you know, what it's attached to, how many it's attached to. And as you can see from this chart, things do have a variety of different oxidation numbers, depending on sort of the situation. So when we think about those charges that we normally associate with certain elements, they really are charges associated in sort of a straight old ionic compound type situation. And that's normally the charges that those guys assume in that sort of situation. But when we get into more covalent bonding things, remember something like nitrate, although it is an ion, it is basically sharing electrons, right, with all those oxygens. And again, those oxygen being more electronegative, going to be bringing those electrons away from the nitrogen, giving it a more positive sort of side than those oxygens that have a more negative side. Any questions on that there?
Yeah, I have a question.
Yeah.
So I'm just a little confused about like what the oxidation number stands for. So it says that it's the charge that the atom would have in a molecule if the electrons were completely transferred.
Yeah.
So if we take like manganese, is it saying that it would rather give up 7 electrons?
It does depend on sort of what it's attached to in that situation and how many. So it depends sort of on, you know, how many oxygens, for example, it's attached to versus versus maybe 2 oxygens versus 3. So taking that into example, say something like permanganate, like we saw with our polyatomic ions. This guy in this situation has attached to 4 oxygens. So again, each of the oxygens here is going to have a -2 oxidation state. Going to give it a -8 overall -1. In this particular case, because it's attached to all 4 of those oxygens, it's kind of sucking the electrons, I won't say completely away from it, but in that sort of arrangement, when it's attached to those 4 oxygens, that magnesium is ultimately sort of not truly giving away 7 electrons, but almost sort of giving away like 7 electrons. And that's different if you take the same Mn and you take the same oxygen, but say maybe only make it MnO2, for example, right? Manganese 4 oxide. In this particular case, -2, -4. In this sort of situation, he's only really giving away kind of the 4 electrons in that case, because there's only really kind of 2 oxygens there to pull basically those electrons from it. So it does have a lot to do with, like I said, sort of what it's attached to, the properties of what it's attached to, and sort of how many, as to sort of what the effective charge, if you want to think about it that way, of like the Mn in that particular molecule or ion. So that's why it varies. And that's why when we think about normal charges, we usually think about charges in just a straight ionic compound. And this is kind of a straight ionic compound, right? No polyatomic ion or anything like this. And we need to go -2 is what we normally think about oxygen. And if you had something like sodium chloride, which is just a straight ionic compound, we can always think, hey, chlorine is going to be -1 because in this case, the sodium is going to completely give away that electron to the chlorine in that particular case. But again, if you look at something like chlorine, you can see it's got a ton of different oxidation states. And it's different when the chlorine hooks up with something like hypochlorite. In this particular case, oxygen is going to be -2. Overall is going to be -1, which means in this case, the chlorine is actually going to take on a more +1 type of charge in that arrangement. Again, here, the major difference between that and sodium chloride is a metal and non-metal, where those properties are so much that it's just going to kind of do the right thing and grab up that electron basically. While when you get the chlorine and the oxygen, if you look at them on the periodic table, they're like diagonal of each other. They have very similar type properties. So again, the best they could do is share it, and chlorine almost takes on like the cation sort of effect in that sort of bond, even though they're sharing the electrons. There's really no complete transfer of electrons. Other questions?
Is that due to one or the other being like more electronegative?
Yeah, it has a lot to do with all those properties we talked about, like electronegativity, electron affinity, size, all those periodic properties that we talked about in that chapter. All those really do sort of play a hand in sort of when they come together, how those electrons are going to sort of be shared, and sort of the almost effective charge that those elements will take in those compounds.
Okay. Last thought to get out is just that chlorine. So you're saying with this hypochlorite, it's not that chlorine has a +1 charge. It's just behaving like it does in that compound.
Exactly. So that's the idea, because remember, again, in something like hypochlorite, they're actually sharing electrons, right? The chlorine and the oxygen. So they're covalently bonding together. But exactly how you worded it there, it's sort of taken on that sort of appearance of sort of losing an electron and becoming positively one charge in that arrangement, which is a very different sort of situation than the chlorine has in something like sodium chloride, where it would actually gain the electron rather than almost behaving like it's giving away an electron in that bond.
Got it. Thank you.
You're welcome. Other questions? Okay. So here's a few more. So let's just go through them and just to make sure. So if we were looking at this sodium iodate here, again, we got 3 elements, and always when you got 3 elements, you should start at the oxygen. So oxygen, again, going to be -2 in this case. There are 3 of them, which gives us a -6. Again, I always go right, go left usually. So sodium, which is always going to be +1. Overall charge here is 0, which means when we put all this together, we got +1 and -6, which is -5, which means we should have a +5 there for our iodine. So our oxidation numbers would be sodium is +1, iodine again is +5. Make sure you include the charge. Oxygen here is -2 on that one.
Wait, Professor, real quick.
Yeah.
How is the charge for that one 0?
It's sodium iodide. So this is really an ionic compound. This is sodium with a +1 charge, and this is iodide, like chlorate. So this iodate has a -1 charge overall. So how we get to the -1 charge overall for just the IO3 part, and that's -1, and the sodium's +1. So this ionic compound altogether has no charge overall.
Okay, I get it. Yeah. Thank you.
And again, if we want to break this down into the IO3 minus, we could see how we get the -1 overall charge for that by applying the same thing here. The oxygen would be -2, which would get you a -6, which means the iodine in this situation, which we normally associate with a -1 charge, actually will have a +5 oxidation state in this case. And that +5 and that sort of -6 gives the iodate part of -1 overall. So again, here in this particular arrangement, as we were talking about earlier, the iodine, which we usually associate as having that -1 sort of charge, because here it's hooked up with an oxygen, which is a nonmetal, and not just 1 oxygen, but 3 oxygens, it takes on sort of the characteristic of having a +5 sort of charge in that iodate compound. Again, even though this is a polyatomic ion, these guys, again, are sharing electrons here and covalently bonding. So taken as a whole, it's -1. That's why when we think about polyatomic ions, we oftentimes just look at the overall charge, because this overall charge here takes into account the individual oxidation states of the elements in that particular ion. So you can look at the overall charge of your polyatomic ion, and you don't necessarily have to worry about each individual one, because that's basically the sum of them all together. If we look at IF7 here, fluorine is always -1, and there's 7 of them, which gives you a-7. Again, no charge on this guy, so it does need to equal 0. So again here, our iodine, like before, would be a +7 in this particular case, and our fluorine would be -1. So again, -1 for fluorine. Do not give the grand total when you're asked for the oxidation number. Just the individual one of those guys by themselves is the correct way to do that. This is potassium dichromate, I think they call that. Again, starting with oxygen, that is going to be -2. That is 7 of them. That's a lot of math there. That is 14. On the other side, we got potassium, which is group 1. So that is +1. There's 2 of them, gives me a +2. Overall charge here going to be 0. Different though, here we don't have just 1 chromium, we have 2 chromiums. So to get us to 0, we have plus 2 and minus 14. That is minus 12. So really to get us to 0, we need a plus 12. And since there's 2 of them, that means each of the chromiums here would actually take on a plus 6 oxidation state. Plus 6 and 2 of them gives us plus 12 for a grand total of 0 when it's all added together. Potassium being plus 1 oxidation state. Chromium being plus 6, not 12. And oxygen being minus 2, not minus 14 in terms of their oxidation numbers. Question on how to assign oxidation numbers. Really important to know how to do this for balancing redox reactions, and more importantly as well, trying to figure out, what is being oxidized, what is being reduced, being able to correctly sort of identify these oxidation numbers, really helpful in that. Any questions on identifying oxidation numbers or states? Okay. So putting this together, we can talk more specifically about different types of really redox reactions. So as I mentioned before, the double displacement, sort of the big umbrella under with, we have precipitation reactions, acid-base reactions, gas-producing reactions. Oxidation or redox reactions, big umbrella, under with we have pretty much all of our other types of ways to classify reactions. So let's take a look at these guys here. First type of reaction is a combination reaction. This is also sometimes referred to as a synthesis reaction. So synthesis or combination reaction is pretty much what it sounds like. When you look at a combination or synthesis reaction, you take 2 things and you make 1 thing, basically. So 2 things make 1 thing is classified as a combination or synthesis reaction. This aluminum plus the bromine to make aluminum bromide. This is an ionic compound being formed. This is a combination reaction. Again, 2 things make 1 thing here. Is also obviously a synthesis reaction. This is also a redox reaction as well. If we look at this, aluminum by itself has an oxidation state of 0. The bromine as Br2, that is how it naturally comes. It also has an oxidation state of 0. When they come together, metal, non-metal, they make our normal charges that we assume. Bromine here has an oxidation state of -1. The aluminum has an oxidation state of +3. So again, if you just kind of think about our number line, aluminum is starting at 0 and ending at +3, which is going to the right. When you go to the right and become more positive, the aluminum is going through oxidation. So the aluminum is basically dumping 3 electrons and going through oxidation. By the way, if you could identify the aluminum as going through oxidation, the bromine has to be the one going through reduction, but just to verify, bromine is starting at 0 and ending at -1, which means it's going to the left, becoming more negative and going through reduction here. And again, what's happening in this case is it's gaining some electrons here and ending up as Br- in this particular case. So gaining electrons, losing electrons, we would need to balance both of these by multiplying the top one by 2, bottom one by 3 to get the same number of electrons, and we would end up here. So this is an example again of a combination or synthesis reaction. And again, although it is a combination or synthesis, it also is under the big umbrella of redox reactions as well. Sort of the opposite of that reaction is the next type of reaction, which is a decomposition reaction. So combination or synthesis, you put it together. Decomposition, you basically break it apart. So you start with 1 thing and make 2 or more things, basically. So combination, put it together. Decomposition, break it apart. And that's what we see here. 1 thing makes a couple of things. Also, this guy is a redox reaction as well. If we look at oxidation numbers, oxygen is -2 here. Potassium is +1. -2 gives me -6 and +1. So our chlorine here, if I did my math right there, is going to be +5. On the other side, this is potassium chloride. So this is a metal, non-metal. So these guys have oxidation numbers we normally think about. So chlorine is -1. Potassium is +1 in this case. And our oxygen is 0. Now, when we look at this, we can see a couple of things happening. Again, if you're not sure, a little number line action here. We look at the potassium on the left is +1, potassium on the right is +1, which means nothing is happening with the potassium. It is just a spectator ion. The chlorine on the left-hand side is +5, which would be over here. And on the right-hand side, the chlorine is -1, which means it is moving to the left. It is becoming more negative. And when you become more negative, it means that the chlorine here is going through reduction. It is being reduced. So this chlorine in KClO3 is going through reduction. While if you look at the oxygen, oxygen is at -2, which would be on this side, and ends at 0, which is going to the right. And when you go to the right, you're becoming more positive and going through oxidation. So our oxygen here is going through oxidation in this particular case. So again, it is a decomposition reaction. It is also a redox reaction. We talked about sort of a decomposition reaction when we were talking about carbonic acid with our double displacement reaction. That guy again breaks apart into CO2 plus some water as well. So, you know, one thing makes a couple of things over here. And another example of a decomposition reaction. So combination, put it together, decomposition, break it apart. Another sort of group of redox reactions are a combustion reaction. And there's really sort of, I guess, two ways to sort of say this, I guess. This is one type of combustion reaction, and your basic sort of general definition of a combustion reaction is essentially you just need O2 to be involved. So pretty much that meets the basic definition of a combustion reaction. I will say that most people, when they think about a combustion reaction, they think about what is referred to sometimes as an organic combustion reaction. And in an organic combustion reaction, you start with something with carbon, hydrogen, and oxygen, react it with O2, which is needed, and you make CO2 plus water. So this is also a combustion reaction, and probably 9 times out of 10, what most people sort of think about in terms of a combustion reaction. But really, a combustion reaction is simply what we see here. Pretty much, you just need some O2 involved for a combustion reaction to kind of take place. So although we usually think about that organic combustion, like when we light a Bunsen burner, propane, butane, methane, all those sort of flammable type of organic compounds, our engines, combustion engines, right? Those are all sort of those organic combustions that we think about. But this basic definition here of oxygen being involved will technically make it a combustion reaction. It is also, again, a redox reaction. The sulfur by itself, uncombined, 0 oxidation state, 0 for our oxygen here. Oxygen on the other side going to be -2, and there's 2 of them, which means that we would need a +4 happening there. So in this particular case, if we want to figure out what's going on, again, if we look at the sulfur, we're starting at 0. And we're adding that +4, which is going to the right. So that is going through oxidation. Oxygen is starting at 0 and ending at -2, which is going to the left. Means it's going through reduction. So this is a combustion reaction. It's also a redox reaction. And some would probably also classify this as what we just talked about. I see 2 things that make one thing. So you could probably classify this as well as a combination or synthesis reaction as well. So again, there's a way that you can sort of classify the same reaction many different ways, sort of depending on what you're looking at. This is magnesium plus oxygen making magnesium oxide. If you ever seen the burning of magnesium ribbon, common experiment they usually do in chemistry. It's the one where they tell you, watch it burn, but don't look at it because you'll see spots in your eyes. It gets very, very bright and it makes this white sort of powder that comes out off of it, which is the magnesium oxide. So again, meets the basic definition here of combustion. Also a combination reaction as well. Two things make one thing. And of course, we were talking about redox. So this is also a redox reaction. 0 and 0 in terms of our oxidation numbers on the guys on the left. Magnesium oxide here, an ionic compound. So -2 and +2. So again, looking at what's happening here. When we look at the magnesium starting at 0, going to +2 in this direction. Again, when you move to the right and become more positive, going through oxidation. Oxygen again starting at 0, heading to -2, going to the left, becoming more negative, going through reduction. And why don't we put everything together here? That would make the magnesium here, since it's going through oxidation, this would be our reducing agent. The oxygen here would be our oxidizing agent in that particular case. Just like above, the sulfur would be our reducing agent. Oxygen would be our oxidizing agent. Question on any of those two. So again, you could kind of see, you could really classify these guys, you know, as multiple ways, depending on sort of what you're looking at. Again, I would say most people, when they talk combustion, is usually referring to this organic combustion up here. But technically speaking, like I said, just having O2 involved in the reaction technically makes it a combustion type reaction. Question on that there. So another sort of reaction that's important is what is known really in most circles as a single replacement reaction. And in a single replacement reaction, the way you can recognize it, again, different than a double displacement reaction is you have one thing by itself uncombined, and this could be typically a metal, or it may be a non-metal. And you have basically an ionic compound. And we've talked about this type of reaction a number of times, I think, over the semester so far. But in general, if this guy is a metal, it again has no charge to begin with. But when metals do gain charges, they do become positive. So it typically will come in and kick out the positively charged ion. And you'll get a new ionic compound that will form, because the A will then gain a charge. The B will come out and actually have no charge on the back end. And this is one type of single replacement reaction. Another type is if the A is a non-metal. And same idea here. The non-metal doesn't have a charge here, but when it gains a charge, it is negative. So it will kick out the negative guy here and will form, again, a new ionic compound, where this guy comes out with no oxidation state on both of these guys here. As I think we've talked about before, in order for this reaction to really take place, whatever is coming in has to be more reactive than what is replacing. So whatever guy is coming in, so in this case, if this reaction takes place, that would mean that A is more reactive than B. If we did this and this reaction did not take place, that means that A would be less reactive than B. So again, whatever is coming in technically needs to be more reactive than what is replacing. Now, the kind of big scheme of these guys, these are really redox reactions as well. They are also under the classification of single replacement reactions. And you could get super specific about classifying this. This is what is sometimes referred to as a hydrogen displacement. This is water. You can kind of think of water like they wrote it in your lab manual like that. And basically what's going to happen is the strontium is going to come in and kick out the hydrogen. When it does, we get H2. So whenever you kick out hydrogen in this type of reaction, you produce hydrogen gas. So you'll see bubbles form, and thus why it's called a hydrogen displacement reaction sometimes. And of course, as we've been talking about here, this is also a redox reaction that's happening. If we look at some of our oxidation numbers here, strontium is 0 in this case. The hydrogen is +1. On the other side, strontium is +2, and the hydrogen, the H2 at the end, is 0. So if we look at the strontium, and again, our sort of number line here of 0, strontium is starting at 0 and ending at +2, heading to the right-hand side. It is going through oxidation, while our hydrogen is starting at +1, which would be here, and ending at 0, which would be going to the left, which means the hydrogen here is actually going through reduction in this particular case. So single replacement reaction, pretty good classification of it. Also going to be classified as strictly a hydrogen displacement reaction. And lastly, can also be classified under the big umbrella of redox. Here is a metal displacement. That's because our metal is coming in and kicking out our metal. Our Ti on the left there has a charge of +4. The magnesium has a charge of 0. And on the other side, it goes to 0 and +2. So again, if you look at something, say like the Ti starting at +4, which is over here, and it's ending at 0, heading to the left, going through reduction in this case. The magnesium is starting at 0 and ending at +2, which is going to the right, going through oxidation in this case. The chlorine is -1 on both sides in this case. Nothing happening with the chlorine. Again, kind of a spectator ion sort of happening in this case. But since we are displacing a metal, it is sometimes referred to as a metal displacement, probably also best referred to single replacement reaction. We also saw this, I think, in an earlier experiment. These are our halogens. Our halogens can replace each other. In this case, this is a nonmetal that's going to replace the nonmetal of the bromine in this case. When it kicks it out, the bromine comes out by itself with no charge. And as you probably can imagine, since it's a halogen that's doing that, this is sometimes referred to as a halogen displacement. Also, a redox reaction happening here. Again, if we look at what's happening in terms of our chlorine is starting at 0 and ending at -1. So it's going to the left, which means becoming more negative and going through reduction in this case. Our bromine is starting at -1 and ending at 0, going to the right, becoming more positive and going through oxidation. And by the way, the potassium here is +1, potassium here is +1. Nothing really happening with our potassium in this particular case. So the overall reaction really is net ionic is the Cl2 plus a couple of bromines with a -1 charge going to the other side where we have a couple of chlorides and a Br2. So net ionic, this is essentially what is going on here. We get rid of all your sort of spectator ions along the way. Question on any of those sort of displacement guys? So you may ask, how do we know if sort of something's going to react or not react in this type of reaction? And there is what is referred to sometimes as an activity series of metals. There's a basic activity series, which is essentially just a column of elements. And when you look at this list of elements, any element that is higher on the list will replace somebody that's lower on the list. And anybody that's lower on the list will not replace anybody higher on the list. Usually hydrogen somewhere in the middle, and then you got guys above hydrogen, you got guys below hydrogen. Here's sort of a fancy list here. We can look at it here, but most activity series looks almost just like the left-hand side, just kind of list of elements. And you, again, anything higher on the list usually can replace somebody lower on the list, and anybody lower on the list can replace somebody higher on the list. So for example here, we look at sort of hydrogen displacement reactions. Hydrogen is a little bit different. In certain cases, you may need water is all you need. Some cases, you need an acid to make it sort of happen. So for example, if we look at calcium and basically hydrogen here, here is calcium. Where are we at there? Calcium, right there. So with calcium, all you need is basically cold water to get that reaction to occur. So this reaction would occur here. The hydrogen would be displaced in that particular case. Now, if we look at lead, which is down here, in order for this reaction to take place, for hydrogen to be eliminated, you actually need an acid. And water is not really a strong acid to make that happen. So this reaction here would actually not take place because of that, because lead would be less reactive than the hydrogen is trying to replace in this case. You would need something probably like hydrochloric acid, then this reaction would probably take place. So there are some rules, but again, a basic activity series kind of looks like the left-hand side of that, where it's just a list of elements. And again, anything higher on the list replaces things that are lower on the list. And vice versa, anything lower on the list will not replace anything that's higher on the list. Like I said, usually in that activity series, hydrogen somewhere in the middle, and you got some elements above and below. We also have sort of an activity series for our nonmetals, and usually it involves our halogens. And as we saw from that experiment, if you remember, group 7 is our activity series. So this is basically group 7 on the periodic table. That's the top of group 7. That's sort of the bottom of group 7. And if you remember from that experiment with the halogens, reactivity in group 7 increases as you go up, where fluorine is. So what that means is fluorine is the most reactive in group 7. And iodine, not so much down on this case. So if we look at this reaction here, which is a single replacement reaction, again, chlorine going to come in and kick out the bromine. So we want to decide, will this take place? So we look at chlorine, and it actually is more reactive than bromine. So we would expect this reaction to take place. So this is a single replacement reaction. Again, it is also a redox reaction, as chlorine is 0. Bromine is -1, and 0. And again, chlorine going from 0 to -1, becoming more negative and going through reduction. Bromine going from -1 to 0, becoming more positive and going through oxidation. And again, here, not much happening with our potassium, really kind of like a spectator ion, +1 on both sides. Now, if we wanted to do this reaction, we would be seeing if the iodine would replace the bromine. And by looking at group 7, we see iodine way at the bottom after bromine. That means that iodine is less reactive than bromine, which means that this reaction should not take place because of that. Again, iodine is going to be less reactive, not going to be able to take place in that particular case. Any questions on that there? Now
I'm sorry. Is that true for all the groups? When you go down the group, it becomes less reactive for all of them?
I would say usually we probably focus mainly on the halogens there, but in general, if you remember just from our sort of periodic trends, right? In terms of sort of nonmetals, the most reactive is found upper right? And the most reactive metals are sort of down this way. So in general, the trend of reactivity, right, like metals kind of increases this way, right, because of those trends, while non-metals, you know, sort of increase going upwards. And that's why group 7, which are non-metals, we see the increase in reactivity going upwards and stuff like that. For example, I think maybe there was like calcium metal in that same experiment, and sodium metal and that type of stuff. And again, if you remember sort of the order of reactivity for that metals that you were looking at, you know, it kind of increased as you went down the group. So again, it does sort of depend on, you know, if it's a metal or non-metal and sort of its placement. So you can't just generally say for all groups going up would be more reactive, because actually when you get to the metals, going down would actually be a little bit more reactive. Other questions?
Got it. Thank you.
You're welcome. Okay, so in addition to the sort of this oxidation reduction, and we've had pretty ones where, you know, it's two elements happening. There's actually cases that it occurs where the same element gets both oxidized and reduced at the same time. And that's what we see here on this last reaction. This is an element that gets both oxidized and reduced at the same time. This is what is sometimes referred to as a disproportionation reaction. And that's a big old word that basically means that, I think, in this case. It is basically the same element that's getting both oxidized and reduced. And it is the chlorine in this case. If we look at the chlorine on the left-hand side at Cl2, it has an oxidation state of 0. If we look at the chlorine on the right-hand side, this guy is -2. And our chlorine in this case would be +1. Our chloride ion here would be -1. And in case you're curious about our oxygen and hydrogen, -2 on everybody and +1, right? So nothing really happened with our oxygen or hydrogens in this case. It really is our chlorine that's getting both oxidized and reduced. You could actually, if you needed to write the half reactions, it would look something like this. You would have your Cl2 that would go to your ClO minus, and then you would have your Cl2 that would go to your Cl minus. So let's think about which one is which here. So in the first one, our chlorine is going from 0 to +1, which is going in this direction. That means that this one is actually our oxidation half reaction, right? It's going from 0 to +1 in this case. And this guy here is going from 0 to -1. This is actually our reduction reaction that's taking place. And we've got here that, and that's oxidation. So technically this guy is giving off electrons. This guy is gaining some electrons. We didn't balance it, but if we balance it, it would be probably 2 happening there. Maybe a 2 there as well, probably a 2 there, and probably a 2 there. And it's basically giving off those electrons. So you can have the exact same element both being oxidized and reduced at the same time. It's very common in atmospheric chemistry. Chlorine happens a lot, and chlorine sometimes gets some of those free radicals where it has just one unpaired electron, making it very, very reactive type of molecules. Any questions on that? So again, potentially possible. Chlorine happens a lot with it, but it is possible the same element in the same reaction can both be oxidized and reduced at the same time. All right, so to kind of finish up sort of classifying reactions here. Again, as we've seen, there's kind of many different ways we could classify some of these reactions. We could talk about some of these here. This is really a precipitation reaction. This is really a net ionic equation. And that's what's left over at the end. They're going to make a solid, which is a precipitation reaction. If we had the whole reaction given to us, you might even classify it as a double displacement. Again, if you had, you know, all the things there, we didn't get rid of the spectator ions. This is an acid-base reaction. Again, basically a proton being accepted here. NH3 is a base. H plus is generic for an acid. And you have basically an acid-base reaction sort of happening here. This is our single replacement reaction. Most specifically here, It is the zinc coming in and kicking out the hydrogen, thus is sometimes called a hydrogen displacement, but single replacement would be fine. And this is a combination, an ionic compound being formed. Two things make one thing. Again, combination or synthesis reaction also, again, could be classified as a redox reaction. Any questions on any of those there? So just to sort of summarize the different ways that we could classify reactions, we had really the big umbrella of double displacement reactions. Which basically followed underneath that general formula of two ionic compounds, where our two positive guys switch partners. And underneath that, we had precipitation reactions. We had acid-base reactions, neutralization reactions. We also had some of those gas-producing reactions. And then kind of the other big umbrella is our redox reactions. And underneath our redox reactions, which usually involves an electron being transferred, we had our combination reaction, our synthesis, we had our decomposition reaction, we had our single replacement reaction, we also had our combustion reaction. Now, the one reaction that you really don't see as redox reactions are these. Yeah, that's why they're under their own umbrella. Yes, double displacement reactions are typically not redox reactions because the two ionic guys switch partners and everybody ends up with the exact same oxidation state. So not usually redox reactions. And all these reactions, again, you could have classify reaction in multiple ways, but they all basically have the three driving forces for chemical reactions: a precipitate being formed, which is this reaction, water being formed, which is basically from like our neutralization reaction, and an electron transfer, which is from our redox reactions. And again, these are the three really driving forces of why reactions take place. One of these three things typically want to be done or formed, and that's sort of one of the, what is referred to again as those sort of driving forces behind reactions. Any questions on any of that there? Okay, so that should finish this little topic, I think. A couple reminders. We had lab, so I think we are up to experiment 8 perhaps. That is about double displacement reactions, so precipitation reactions. So that should be pretty straightforward. We'll talk about that when lab starts. A reminder again that our exam is on Tuesday. And again, it's on those chapters. You remember those chapters, but those are chapters, I think, about bonding, nomenclature. So that should be 3, 4. Also should be, I believe, 5. And that is 5 that covers moles, Avogadro's numbers, empirical and molecular formulas. So we'll do what we normally do. We'll have a short little lecture on Tuesday. Then you can take the exam during lab period like we normally have done. Any questions on any of that stuff coming up? Okay.